Good day, students. Welcome to Schoolonair. I'm going to take you physics this today, and the topic of discussion is area and cubical expansivity. When we are talking about area of cubical expansion, we treated linear expansivity in the last class, and we were able to solve some examples. We analyzed some formula, and we were able to apply the equation that we used in solving the question that arise from the topic that we treated. And today we want to continue from that our last point of discussion. So we are starting with area or cubical expansivity today. When we're talking about area expansivity, it is the increase in area per unit area per degree Celsius rise in temperature. This is a little bit related to the previous discussion that we had when we were talking about linear expansivity. In that case, we spoke about the expansion in the length. But in this case, we are talking about the expansion in the area. The difference is, when you're talking about area of a material, you are considering not only the length, you are talking about both the length and the breadth involved. That's why we are talking about the area. In the previous class, when we treated linear expansivity, we spoke only about the length. Just one side expansion. In this case, we are talking about expansion in two dimensions, that is both the area, both the length and the breadth. So area expansion, it is the increase in the area per unit area per degree Celsius rise in temperature. That is the definition of area expansivity. Now, having said that, we proceed into the expression. That is, if you have a question under area expansivity, if you are told to define it, we've just given the definition. After the definition, the next thing that can come under this kind of a topic is you talk about the calculations. That is, if you want to calculate the expansion that are taking place in terms of area of any material, how do you proceed? This is the expression. The equation is area expansivity. We denote it in physics by beta. I said in the previous class that if you want to we denote linear expansivity with the symbol alpha, but in this case we denote area expansivity in physics with the symbol beta. So area expansivity beta equals to what? Increase in area all over what? The original area times temperature rise. What are we talking about? I explained to you how to get increase in length in the previous class. In this case, it's just a matter of the difference is we are talking about length, then we are talking about area now. The increase in area in this case means the final area, that is the new area you obtain after the expansion. You deduct the initial area from that will give you the increase in the area all over the original area, that is the former area that you are having before the expansion took place, times the rise in temperature. That is the combination of this formula you are having here. And the symbol for this is A to represent the what? The new area. A1 represent what? The initial area, and A1 here means the initial area times delta theta, which is what? A small rise in the temperature, equals to what? Is equals to what? Beta, which is area or superficial expansivity. Now, having known the formula, now we proceed by trying to rearrange the expression. If you are calculating the increase in area, what do you do? If it is the increase in area you are told to calculate from the question, if you are given any question in any examination or in any test, if you are told to calculate the new area, what do you do? The increase in area, what do you do? Increase in area is this, that is A2 minus A1, that is new area minus the initial area, equals to area expansivity times the old area or the initial area times rise in temperature. This gives you what? The increase in the area. A2 minus A1 denotes the increase, because by the time you deduct the new from the initial, you deduct the initial from the new, you are going to get what? The increase that has taken place in the area of the material. So this is the formula for calculating the increase in area of any material when you are talking about area expansivity. But if it is the new area alone we are told to find, not the increase, then you need to use this. In that case, you are talking about A2 alone, which denotes what? The new area, which is what? Old area or the initial area plus area expansivity, the old area times change in temperature, which if you rearrange it by mathematically by making by taking out the A1, you will have A1 equals to A1, A2 equals to A1 bracket 1 plus beta delta theta. That is, the new area equals to the old area into bracket 1 plus superficial expansivity or area expansivity times rise in temperature. So when you rearrange that, you have what we have here, because the only difference between this and this is that what beta, which we have said that it is the same thing as twice the increase in the alpha. What am I talking about? Beta denotes increase in area. It denotes area expansivity, area expansivity. And alpha denotes what? Linear expansivity. So when you are working any calculation, you should bear it in mind that if you are given the linear expansivity and they are not talking about, you are told to calculate the area expansivity, know that twice the area, the linear expansivity will give you the area expansivity. So if you are given only the linear expansivity and you are told to calculate the area expansivity, multiply that value you are given for linear expansivity, that is alpha, multiply your alpha by 2. It is the same thing as what? Beta. That is what we are trying to show here. And that is what I've stated here, that since beta is always equals to 2 alpha, definitely this expression and this expression means the same thing. The only difference is what? We have substituted for beta here 2 alpha. That's all. That's the difference. So this is the new area. Having said that, now we will need to do some examples to back up to give a further explanation on what? On the equation we have just derived. This is a typical question that you might be facing in an examination. Question 1. A square metal plate of size 12 cm is made of a material of linear expansivity 2.5 times 10 to the power minus 4 Kelvin. Per Kelvin. Now, this is a square metal. You know what a square means. You understand me? A square is what? You know what a square means. Now, it's having a side of 12 cm and it is made of a material of this linear expansivity. What are we now going to do? The question is now telling us that if it is heated from a temperature of 27 degrees centigrade to 120 degrees centigrade, what will be the area of one face of the plate at the highest temperature? The highest temperature from the question we're having here is what? 120, as you have seen it here. This is the highest temperature. This was the initial temperature of the material before the expansion took place. Now this is the new temperature. Definitely at this temperature, what will be the expansion that has taken place? That is what the question is telling us to calculate. How do we go about it? We shall see soon. This is the formula. The solution goes like this. Beta represents what? The area expansion or area expansivity, which we have said earlier that is equals to what? Twice alpha, that is twice the linear expansivity, which is equals to what? The increase in length in area all over the original area times change in temperature. We have been given this in the question that what? The expansion that is taking place, the linear expansivity is 2.5 times 10 to the power 10 minus 4. Multiply by 2. Because this is alpha, this represents alpha, this 2 is the one we're having here. Equals to what? The new area minus the initial area. We are using 12 by 12 here. Why? When we are dealing with linear expansivity, we only need to use this one once. But in this case, we are dealing with area. And since the shape is square, is a shape of a square, the area of a square is what? Length times length. Because the shape of a square is what? All the lengths are the same. So without being told, mathematically, you should know that what? You need to have 12 by 12 here. If it is in the shape of a rectangle, then this wouldn't have been applicable. We wouldn't have been able to multiply the 12 by 12 here, because definitely if it is a rectangle, the shape of the length will be different from the shape of the length will be different from the breadth. So we will not be able to have 12 by 12 here as we are having it here. See, but since the question told us that it is in form of a square, as you can see from what the question has said, that what? A square metal. That is what this time is trying to point out to us, that the shape of the metal is in form of a square. Since it's in the form of a square, then we are free to use to duplicate the length. You understand? That is why we are just duplicating it here, that our own area is what? 12 by 12 all over the initial area, which is 12 by 12 times what? Rise in temperature. This is the change in temperature, final minus initial. Now if we work this out mathematically, you will have what? By the time you cross multiply and work this out mathematically, A2 gives us what? You cross multiply. 12 by 12 gives us 144. So you have A2 minus 144 here. That is what we are having here when you cross multiply. Then this 2 times 2.5 times 10 to the power minus 4 comes here to multiply what you are having here. Then you are having this expression as we are having here. If you work it out, 120 minus 27 gives us 93. This 12 by 12 gives us 144, and this is the arrangement that we are having now. Now you take this minus 144 to the other side of the expression, it becomes plus. Then when you work this one out, this one, you will have what we are having here as a value. So by time you add this to this is what you have. You can press your calculator to confirm this. So this is the solution to that particular question. I believe this gives us a sort of insight into what we need to do if we are to calculate the area expansion in any material. It is as simple as this. It is highly related to linear expansivity with some little differences, like multiplying, knowing what to do here. In case you are given that the shape is rectangular, you should know what to do, that you cannot duplicate it like this here. Then in the case of linear expansivity is linear expansivity. But in some cases under area expansivity, you will not be given the area expansivity, you will be given the linear. You should know that you multiply it by 2. Then every other step is similar to what we treated in the last class when we were talking about linear expansivity. I think this gives us an insight into what we are discussing about under area expansivity. Thank you. Now, having said that, we need to proceed into the other aspect of the topic, which is what? The volume or cubic expansivity. What do we mean by volume or cubic expansivity? Volume or cubic expansivity is also related to linear and area in terms of definition. The difference is, under volume expansivity, volume or cubic expansivity of a liquid is what? Is the increase in volume per unit rise in temperature. Under area, it is what? Increase in what? In length. Under area expansivity, it is increase in area. Under volume expansivity, it is what? Increase in volume. That's just the difference. And you know the difference between length, area, and volume. In the case of volume expansivity, you need to consider the length, the breadth, and the height. You understand? So increase in volume, per unit rise in temperature. That is definition of volume or cubic expansivity. Now, we need to get the formula. And what is the formula for calculating volume or cubic expansivity? That is what we're having here on the board. Volume expansivity denoted by gamma. We denote linear expansivity with alpha. We denote area expansivity with beta, and we are denoting volume expansivity. That is the standard in physics. It's not peculiar to any part of school or nation or anything. Volume expansivity denoted by gamma. Gamma volume expansivity equals increase in volume all over what? The original volume times rise in temperature. And volume expansivity is 3 times linear expansivity. Area expansivity is 2 times linear expansivity. Volume expansivity is 3 times linear expansivity. That's why we are representing gamma here with 3 alpha. So if you are given alpha in a question, you multiply by 3, it gives you what? The gamma, which is the volume expansivity, which is new volume minus initial volume all over initial volume times rise in temperature. This is the formula. If you work this one out, what are we going to have? You will have this. If you want to calculate the increase in volume, this is the increase in volume. Final volume minus initial volume equals to 3 times linear expansivity times initial volume times change in temperature or rise in temperature. New volume, if it is the new volume you are looking for, the new volume V2 is initial volume plus 3 alpha V1 times change in temperature. Then V2 gives you, by the time you work this one mathematically, you factorize, V2 gives you V1 into bracket 1 plus 3 alpha times delta theta. Having said that, let us see one example before we leave. Now, this is a typical question that can come out, or you could be told to calculate. A liquid of volume 80 centimeter cube at temperature 20 degrees centigrade expands to 80.8 centimeter cube at what? 40 degrees centigrade. It was initially at 20, is now at 40. Expansion has taken place from 80 to what? 80.8. What is the new cubical expansivity of the liquid? How do we go about it? That is the solution here. You are having the formula 3 alpha, which is same thing as gamma. That is the cubical expansivity, equals to change in volume over original volume times rise in temperature. 3 alpha equals to what? Gamma, which is, we substituted the values we are having here from our question, and this was the old volume times rise in temperature, 40 minus 20, final minus initial. When you work this one automatically, this is what you are going to have as your answer. This is a part of present calculator. You understand? So we have successfully discussed 2 important aspects today. We did a sort of recap on linear expansivity. Today we have discussed area expansivity and volume expansivity. We have been able to give the formula, and we have been able to solve some examples. So having done that, I believe you should have a sort of pre-knowledge on what to do if questions come up in area or cubical expansivity. But I will not leave without giving you a sort of assessment to assess what you have learned today. Now, this goes for my assessment question. A gas occupies a certain volume at 27 degrees centigrade. At what temperature will its volume be 3 times the original volume, assuming that its pressure remains constant? You are having a gas here. You understand me? This is it has a volume at 27 degrees centigrade. You understand me? The temperature has increased or it has reduced. They are not telling us. The question just says, at what temperature will its volume be 3 times? Common sense will tell us one thing, although we are not told whether the volume rose or whether the temperature rose or reduced, but we are told that the volume is 3 times. As we have discussed in our previous classes, something should tell us that what? The temperature must have gone up, because the volume has increased, and we discussed that what? When we are doing kinetic theory, that what? When you heat a material, gas will what? They will expand. You understand? When you supply heat. So for the volume to have been 3 times, definitely the temperature must have risen. So you should expect an answer that is more than 27 degrees centigrade. So, and that is the question, and I believe that with this information, you should be able to solve this question with little or no challenges. If you have any question, you can send it to the address you're having on the board, and that brings us to the end of the class. Thank you.